Hello, this is Mrs. Butcher, and this video is on variation functions and mathematical models. Alright, we're going to be learning about two different types of variation functions, and that's going to be direct variation and indirect or inverse variation. Direct variation, you're going to see it written y varies directly with x. Sometimes you might see y is directly proportional to x, but when you see that, you're going to use this general equation. Y equals k times x. Sometimes you'll see something else for the k. I think our book uses an A. It doesn't really matter what letter you use. That is the proportionality constant. We'll also deal with functions that are inverse, and it would say y varies inversely with x, and sometimes you might see y is inversely proportional to x, and that looks like this. Y equals k divided by x, and k is, again, your proportionality constant. So the important thing to remember is when you see y varies directly, or anything varies directly, you think k times, and when you see anything varies inversely, you think k divided by. Alright, let's do some example problems. Alright, y varies directly with the square of x. So you're going to write y varies. You're going to say y equals. You see directly, so you're going to put k times. And then the square of x would be x squared. So that's how you would translate that. Alright, the next one says y varies inversely with the square root of x. So that one would be y varies. You'd say y equals. Inversely, k divided by. The square root of x looks like this. And I used square of x and square root of x in my examples because they're commonly mixed up. People see the word square and they think square root. But if I want the radical, I'm going to use the word root. Square of means to actually square the variable. Alright, this next example is actually problem number 1 on the variations function worksheet that I will give you guys tomorrow. And that problem says, the number of pounds you weigh is directly proportional to the number of kilograms you are. K. Dents steps onto a scale calibrated in kilograms and finds that she is 50 kilograms. She knows she weighs 110 pounds. So before we do anything else, we are always going to define our variables. And by define, I mean write them down. If you're going to use a P for pounds, that's fine. P is going to be the weight in pounds. And then we have mass is what the kilograms are measuring. So I'm going to use an M for the mass in kilograms. You can't just pick variables and use them without defining them on the page for the reader to know what you're talking about. Okay, the first part of this problem asks us to write the particular equation expressing pounds in terms of kilograms. So in order to write this particular equation for this particular problem, first we need to set it up. We know that it says pounds is directly proportional to kilograms. So we're going to say P equals, and directly is K times, and then kilograms is our mass. You have to have a proportionality constant in there. Now, they gave us some numbers in our problem, so we're going to plug those numbers in. It says that K weighs 110 pounds, so I'm going to put 110 for the pounds. We don't know the constant yet, but we do know the mass that goes with 110 pounds, and that's 50 kilograms. So 110 equals K times 50. We're going to divide both sides by 50 and get K equals 2.2. So then when it says write the particular equation, you have to go back to this and rewrite P equals, and then instead of K, you put the number that actually belongs there, 2.2, and then M. So that's the equation. Now we know how to convert pounds to kilograms. Alright, the next part of this problem asks us, how many pounds would a person weigh if the scales read 100 kilograms, 25 kilograms, or 150 kilograms? So now we have 3 different parts we want to figure out, but we already know our equation. Pounds equals 2.2 times the mass. So we could solve for 100 kilograms just by plugging in a 100 for the mass. P equals 2.2 times 100, which is 220 pounds. 220 pounds, sorry. If they weighed 25 kilograms, a 25 kilogram per pound, 25 kilogram person would be 2.2 times 25 is 55 pounds, so that's a small kid. And then 150 kilograms, we do P equals 2.2 times 150. And you would come up with 330 pounds. Big one. And always write your units. Some of you got zapped by that on the last test. Always write your units. Maybe put yourself a note in your notes. Units. All right, this next part says how many kilograms would stand up be if he weighed 165 pounds. So now they're giving us the pounds, so we plug 165 in for the P. 165 equals 2.2 m. All you have to do is divide both sides by 2.2 to get that Stan's mass is going to be 75 kilograms. Don't forget your units. And the last part of this problem says, what quantity does the proportionality constant represent in the real world? So remember that proportionality constant, that was what K is. And we said K was 2.2, but we didn't put any units with it. So if we go back and we said, okay, our pounds equals K times our mass in kilograms, and then we just divided both sides. We divided our pounds by our kilograms. So that means that your K, the units, is going to be pounds per kilogram. K represents, and you write it in a full sentence, K represents pounds per kilogram. And that's how you do those kinds of problems. This last problem is a mathematical model example. It's not necessarily a direct or inverse variation type of function. So this one says, you are driving home from a friend's house on the other side of town. When you are 11 kilometers away from home, you have driven 10 minutes. When you are 8 kilometers away, you have driven 15 minutes. Assume linear variation. So that means we're just dealing with y equals mx plus b, no squareds or anything like that. The first thing we want to do in all these problems, like I said in the last one, is always define your variables. So for this problem, we have 11 kilometers away from home. I'm going to go with a distance, and then we've got 10 minutes time. So I'm going to let x be time because time is independent. X will be time, and y will be our distance. Once we figure out what we're working with, we're going to pull ordered pairs out of the problem. So in this case, we know that the first ordered pair is 11 kilometers in 10 minutes. So that goes 10 because time is the x, comma, 11 because the distance is the y. And then the second one is going to be 8 kilometers away is 15 minutes. So time is the x, 15, and the distance is 8. So those are two ordered pairs from our problem. Now we did a bunch of problems earlier where you were given two ordered pairs and I asked you to write the equation. That's exactly what we're doing now. So before we can write this equation, we need to find the slope, also known as rate of change. In this case, because it's a word problem, it is a rate of change of kilometers per minute. So our slope, we're going to go y2 minus y1 over x2 minus x1. And that gives us a negative 3 over 5. Why is that a negative slope? Because you are decreasing your distance. You're getting closer. So the rate of change in our distance per time is getting smaller and smaller and smaller as you get closer and closer to home. So the fourth thing I have in my list of stuff to do is to think about what that slope means. And I just kind of talked about that. But we know our rise over our run, which is always your y over your x, your change in y's over your change in x's. That's kilometers per minute. So it's the speed, basically, in this case, your speed. Okay, next we're going to write the particular equation. And when I say particular equation, I mean the one with numbers in it. Now we know the slope, so we're going to I'm just going to do point slope. Y minus y1 equals your m, and then x minus x1. And it doesn't matter which point you use. And my, this problem doesn't say it has to be in slope-intercept or any other form, so this is perfectly acceptable as long as it doesn't tell you what form to write it in. So there's the particular equation. The next thing I want to do is plot a graph of it. A lot of these word problems are going to ask you to graph them. For this problem, I'm not going to have any negative time and I'm not going to have any negative distance. So I'm just going to do a positive quadrant. Now don't forget to label your axes. We always want to label. So on the x-axis it's time driven in minutes. And on the y-axis we have the distance from home in kilometers. And we'll start with 0. Now we know two ordered pairs, so we could plot those on the graph. We've got 10, 11, and we've got 15, 8. So we kind of need to think about how far out we want to go on this graph. We would kind of want to calculate, okay, where's the y-intercept, where's the x-intercept, where's this going to hit? Just to go ahead and go on with this problem, let's count by 2's on here. 2, 4, 6, 8, 10. So we know we have a point at 10, 11. 2, 4, 6, 8, 10, 11. That'd be there. And we know we have a point at 15, 8. So 12, 14, 16, there's 15, and 8 is there. Oops. Put it closer to the middle. There. So we know we have a line through these 2 points. We know our slope is negative 3/5. So you're going down 3 and over 5, down 3 and over 5, like that, down 3 and over 5, down 3. I mean, you could just draw it on there. And make it a mess. Okay, but here's our graph. Here's a much prettier version, one with a straight line and actually plotted correctly. But there's our graph. Alright, and then they might ask you some questions about it, like how much further do you have to go when you've been driving for 25 minutes? Well, now that you have your equation, you can just plug numbers in. We've got y minus 11 equals negative 3/5 times x, which our x is our time, and so now we're going to plug in a 25, and then minus 10. So you just plug that in. You'll have to add 11 to the other side, but we're going to end up getting 2. And since our units are kilometers, 2 kilometers is the answer. I might ask you something like, when do you get home? So you have to think, well, when you get home, that means your distance from home is 0. So we are going to plug a 0 in for our y value. We want to know, when is 0 minus 11 equal to negative 3/5 x minus 10? So if we multiply this out, we've got negative 11 equals negative 3/5 x plus 30 divided by 5 is 6. So if I added 6, if I move this over here, 3/5 x equals, added that over here, I'd get 17. Of course, the bell's going to ring in the middle of my presentation. But that gives us x equals 28 1/3 minutes. That's how long your trip takes. So 28 1/3 minutes after you left. And the last thing I'm going to ask you about this example is what domain and range would give you valid real-world answers. And I went ahead and put a picture of the graph, the same copy of the graph, on here that we did earlier, because domain and range, it really helps a lot of us to see it visually. And we talked about the whole valid real-world thing when we made the graph, because we didn't give any negative time, and we didn't give any negative distance. So we actually have closed circles here and here instead of arrows. And so that means that our domain for the real world is actually just the segment. Let's do domain. Domain, our x is our time, starts with 0, and we will touch 0. You can not drive. Oh my goodness. Well, again, you guys are probably freaking out. Okay, and then if you look, the highest x value, we already figured that out. It was 28 1/3, because that's when you get home. So that would be your domain. Now your range would be the lowest y, which we're also going to say is 0 miles. And then the highest, if you look on here, I've already figured out my y-intercept, but you would just need to plug in a 0 for x to solve for your y-intercept, and you would get 17. And it could touch that. So that domain and range would be valid for the real world in this problem. And I'm going to call it quits now. So you guys have a good night. Bye.